Okay, here we are with the last video on the fourth big idea dealing with the sampling distributions of a sample mean and a sample proportion. And the theorems that we talked about in the overview video was the central limit theorem for the sample mean and for the sample proportion. Now, um, I did do more of this and got into all in depth of where this is and what it represents and so forth, but the big idea here is that if you have a random variable that has any distribution, I kind of kid around, like I said in the video in my other courses, any old way, meaning any way, could be normal, could be whatever. Um, then the distribution of the sample mean is going to be also normal, okay, or it will be normal, or at least approximately normal. Now, if the population's normal, then this will be exactly normal. But for right now, we're just going to say any distribution. It'll be approximately normal, and the mean of the X bars or the sampling distribution will be the same as the mean of the population, but the standard deviation will just be this. That is the standard deviation of the population divided by the square root of the sample size. And if this is really bizarre distribution, again, what we said is these were kind of some Lambert numbers if it was off a bit, but the more normal this is, the more normal that's going to be. But to negate that, if we have larger sample sizes, then we're going to still be okay with this normal thing. And ultimately, what we're going to do is find a probability with this given relationship here. So getting into this problem here, it just says, we have a situation where alcohol withdrawal occurs to when a person uses alcohol excessively and then suddenly stops. Okay, studies shown that and this would be referring to the population, 39.5 hours, okay, after the last drink, and with a standard deviation of 17. Now, the sample of 38 people is what's taken. So in other words, this is mu, this is sigma, and that is n. So we're going to use this relationship over here that I mentioned. Try to drag that over so we can see it. Okay. And really all we want to do is just, calculate a probability. They don't tell us the distribution of the population, which is okay due to the central limit theorem. We just know, it can be really skewed strongly. And I get into that in the video illustrating that, in the other video, I should say. But since we know we've got at least 30 people, 38 is definitely greater than 30. So we're just going to do regular normal calculation here. Okay. So first thing what we want to do is calculate what the standard deviation of the sampling distribution, right? Because we want to know the probability that the sample mean time, that's the X bar, an individual observation is X. Well, this is X bar, okay? What it would be 38 hours or less. So I'm going to find that standard deviation. I know the mean is going to be the same, 39.5, but the standard deviation is going to be 17. Divided by the square root of the sample size, which in this case, again, is 38. So I got about 2.7, let's say 2.76. So we'll go to two decimal places and see it rounds three decimal. Well, let's just say 2.76 or no, 2.758. And it's not going to make that big of a difference with this rounding error with this calculation. Okay, so 2.758. So what I'm going to do then is I am going to jump into my, if I can find it. Oh, here it is. Okay. And I am going to put those means and standard deviation in. I say 2.578. Let me just make sure I did that correctly. Enter that in correctly. 2.758. 2.758. Okay. And the mean again is going to be 39.5. All right. So now, what is the probability the sample mean time will be 38 hours or less? So that's pretty straightforward. That is going to be a value to the left of 38 hours. Okay, so I am going to type in 38 and I'm going to calculate that, and it turns out to be 29.33. Since I want that to 4 decimal places, this should be rounded here. So I'm going to enter that as a decimal as 0.2933. Type that in, 0.2933. We check our result, and there we go. We did it correctly. Okay. Now, obviously, that could also be done on this sheet as well. If I enter in those values here, the mean was 39.5. This is my Excel spreadsheet, obviously. My standard deviation, I have to go back to this 0.2758. 2.758. I think I said that wrong, but I think I typed it in. No, wait, there it is. Yeah, 2.758. And my data value is 38, I believe. And so there we go. And you can see now a probability to the left of that would be 0.293. You know, and if I did the standard normal, that would be the same as the area to the left of negative 0.54387 on the standard normal curve. Okay, but so there you have it. And actually, they report the Z value here as well, just rounded to 3 decimal places. Okay, so those would probably be the way I would go about that. Obviously, you could even still use the normal calculator to calculate that value, but you'd have to use the Z value. And I think you again can see that's involves some step there of calculating the Z statistic first if you didn't use one of these. Okay, we kind of cheated here. It does that automatically where it just takes the X value, which is 38 minus this and divided by the square root to get this Z value. Okay, so that is the central limit theorem for a sample mean. Okay, we will, let me just jump into the other type of problem here. And there's some other ones here, you know, like I said, these are like just maybe part of this comprehensive problem. I just wanted to do the comprehensive ones. All right, so let me get into one with the sample proportion. And it's going to be the same type of problem, with the exception of, if I get into this, is that the okay, that for the sample proportion now, we're dealing with a percentage, right? Or we, you know, count the number of yeses, nos, whatever. And the if these conditions hold, if the population is greater than 10 times the sample size, and n times p and n times 1 minus p are both greater than 10, then this is going to be the sampling distribution. So again, it's going to be a normal calculation that we're going to compute here. And this is going to be the mean, that's the standard deviation. Okay, so they're just basically going to give us two numbers, n and p, and then from that, we're going to find out what that distribution is. And then they'll also give us information, you know, to find the sample proportion. So let's take a look at this. And okay, so this is a problem, except they're dealing with painkillers, right? And so right here, they're telling us that for a special type of painkiller, the symptoms occur in 4% of the cases, right? Now, that again is for the population. So now we get a random sample of 2,400 people. Okay, so I think it's safe to assume that if I take, you know, first of all, the population of people that would take this would be more than 10 times this. So that would satisfy this condition. And then obviously this n, which is this times p, and n times 1 minus p, that's clearly going to be, we're not going to figure it out, but we know it's more than 10 when I multiply 2,400 times 0.04. I'm going to get 10 or more easy. So, so what this is doing here is actually, if I slide this over, maybe we can look at both those at the same time here. It's asking us, okay, what's the mean of the p hat? Well, the mean of the p hat, and again, remember, I do more of this in the other video. But the mean of the p hat is just going to be p. So all we have to do is type in here 0.04, okay, because that's 4%. And usually they, again, even though they're listing it like this, let's just enter those in unless they tell us the type of percentage, and we'll deal with the decimal representation. Now, the standard deviation is going to be a little bit more of a calculation here, so I will go ahead and type that out here. So I'm going to type the numerator of the fraction. So I'm going to put in here 0.04, and I'm going to multiply that by 1 minus 0.04, which would be 0.96. Could have typed that all out if I wanted to. And then I'm going to divide that by the sample size here, which is 2400. Okay, so the mean is just whatever P is. I already entered that in. The standard deviation of the sampling distribution of P hat, okay, is going to be this. So I'm going to type that in, and I get 0.004. I'll go ahead and enter that. And now what they're asking me is, okay, so let's compute approximation for the probability of getting a sample proportion of 3%. So out of this, we want to know how likely it is that out of all these 2,400 people, what's the probability that 3% of them are going to be, or what's the probability of getting a sample percentage here, okay, of 3% or higher? Okay, so that's what we're looking for here, a P hat. That would be the percentage in the sample out of these, okay? So I would take the number of people that have, you know, whatever I want to say, the withdrawal symptoms, right? Okay, you know, if it was 5, it would be 5 divided by 2,400, and that would give me our percentage and so forth. Okay, so I want to know what the probability of getting 3% or higher of those people getting painkillers or experiencing withdrawal symptoms. So again, I go to my normal calculator because I know that's a normal probability here because it has a normal distribution. So I'm going to jump into that, and by doing that, let's just use the slide this out of the way. Move that down here, and then we'll go behind here. Okay. So I'm going to put my mean in here, which is 0.4 or 0.04, and my standard deviation, which is 0.004. I put in my data value of 0.03. Right. And I get that probability of a right probability and a left probability. So chance of that happening is over 99%. Okay. So they want 4 decimal places here. So I will put in 0.9938. Okay. So, you know, of getting more than 3%. Now, again, that kind of makes sense, right? On average, you know, we're going to get 4%, but, you know, to go as low as 3, and this is a very, very small standard deviation. So it's almost like we're guaranteed that that would happen, okay, to get a sample proportion of, you know, 3% or higher. So, you know, out of this, we're going to get 3% or higher, more of these people. We're very likely for that to happen. I just, you know, that's all you would have to do here. I'll just go ahead and check that result just to show you that we are correct with that. And then I'm going to go back here, and I'll tell you what, I'm just going to minimize that right now and get that out of the way. I just want to show you, you know, again, we can do this on Staplet, which I'm sure you know that. But if you didn't see the other videos here, so let me put in the 0.04 and let me put in the 0.004. Okay. And I'll plot that distribution. And now I want to go to the right of a value. Okay. And that value is going to be 0.03. And I'll calculate that value. And you can see that's that 9938 or 0.9938 or 99.338% chance. Okay. Which again is very likely, almost certain in that instance. So there you have it. These are relatively straightforward, and you know, it is just, you know, one of these things that, you know, I'm just going to kind of soft introduce this idea of hypothesis testing. Okay. Let's just suppose this wasn't 4%. You know, let's just say we ended up, you know, let's say out of the 2,400 people, let's just say we found that we had 5%. Okay. that had side effects. All right. Well, the chance of that happening is 0.62%. Okay. So that's very unlikely. Now, if you go back to this and say, well, how do we know 4% of every single person has side effects? Because a lot of times things like that aren't reported. Nobody collects that at a central location, that sort of data. In particular, medical information is very well guarded and so forth. You got to agree to share that information, and that's where clinical trials come in. So let's just say again, we're looking for a drug and for its acceptable level of side effects, and for whatever reason, let's just say, hey, you know what, 4% we're okay, and or less than that. That's acceptable in the industry. Now, I don't know if that is or not, but given all of the risk of not being addicted here, this is kind of an interesting example here. There's going to be some sort of risk, and we're not going to know what this population percentage is. So what we actually do is formulate a hypothesis, and let's just say the experts say, hey, you know what, we can live with a 4% people having withdrawal symptoms. We can treat those, and that's not that many given the benefits of the drug and that sort of thing. So all of a sudden we go out and we get 2,400 people volunteer, and we randomize, and we'll get into experimental design later, but let's say there were actually 4,800 people, and 2,400 received placebo or nothing, and the other 2,400 got a the new drug. And so however we set that up, or the experts set that up, the bottom line of what I'm trying to get at here is that if we got 5%, that would be really unlikely to happen if this in fact were true. Now remember, we don't know what that is in actuality in real life, so we make a hypothesis or an educated guess, or in this case, this is a landmark we want to hit, and we get 5%. Well, if this is really true in the whole population and we get 5%, that's really unlikely to happen. So what does that say about this hypothesis, or this this value right here, the true value of the entire population? This is going to be evidence against that, and chances are that this percentage is actually going to be higher than what we wanted it to be. Okay, in order for us to get these results, in other words, a sample mean or sample proportion of 0.05. Okay, so that's what we got. We're just saying that that's what we got. 5% of these people had side effects, okay, or withdrawal symptoms. Well, that's pretty unlikely, and therefore we can conclude that probably the true percentage or value for P is going to be more than or higher than 4%. And so that's just, we put that more into formal language later on when we deal with hypothesis testing. But for right now, a lot of times you'll see the phrase, it was statistically significant, in other words, we have enough evidence to suggest that it is really higher than 4%. Okay. We don't know what it is. We can use methods of estimation, which we'll get into later on as well. But that's just kind of a soft introduction to what we're going and why this is important to know this information. All right. So again, because everything we do on now for in the practical sense, as we get later and later or more into the course, is going to be based on this foundation. So if you had to really, try to identify, the foundation of what it is that we're doing when we do statistical analysis and research and so forth. All of these calculations, these probability calculations, are going to be important. And to do these techniques that I just kind of alluded to with the hypothesis test, and those are all based on the idea of a sampling distribution. Okay, so that's why that's such a big idea. All right, so anyway, so I hope this video is helpful, not just for this particular problem, but also for where we're going in the rest of this course. So that's going to be it for this week, and God bless, and we'll see you next week with the week 4 information.